Here we've got a diagonalizable matrix A, and then we're actually told a little something about the eigenvalues. They're either 0 or 1 for all of them. And we should be able to use this to show that A squared is equal to A. So just as our starting point, what we'd want to do here is use this property of diagonalizability. And what that means, turn it into a math equation that can be manipulated. So that means there's some invertible P that turns this thing into a diagonal matrix. So P to the negative 1 AP is D, where D is diagonal. And then now we're going to use the 0, 1 property here so that D, in fact, is something of the form, we can call it like lambda 1 all the way down to lambda n, and we don't know how big it is. Zeros here and zeros there, where lambda 1 through lambda n are zeros or ones. And so now if I look at A squared, it has obviously something to do with A, and we're going to want to use this diagonalizability property. And then we also want to use what we have from D here, and well, particularly if we note that if the lambdas are all zeros or ones, then when I square them, they don't change, right? So they're 0 squared or 1 squared. So what we actually get is that lambda 1 squared is lambda 1, right? All of them are going to actually satisfy that if I square 0, it doesn't change, and if I square 1, it doesn't change. So we have this really nice property that when I square them, they don't change. So actually D squared is D. And that's where we're actually going to be able to get our A worked back in. So if D squared is D, then what I've actually got is that plugging these things back in to the D's is pretty much going to resolve our problem. So that means that P to the negative 1 AP squared equals P to the negative 1 AP. And if I expand this thing on the left, it's P to the negative 1 AP, P to the negative 1 AP is P to the negative 1 AP. And this allows us to reduce that middle, right? These are just going to be I. And so what I actually have here is P to the negative 1 A squared P is equal to P to the negative 1 AP. And now because P is invertible, we can basically cancel those things off. And we would do that by just left multiplying both sides by P, right multiplying both sides by P to the negative 1. And what we're left with when we do that is actually A squared equals A. And that's it. That's the proof. And that's how those two things are related to each other, just because diagonalizability means that we can pretty much do a lot more operations on our matrix easier, particularly powers.